Section 2.5, heat capacity. What is heat capacity? It's the amount of heat required to cause 1 unit change in the temperature of a system. So heat capacity C is equal to dQ over dt. dQ depends on the path or process. Q is a path function. Therefore, C also depends on the path or process. There are many different processes: adiabatic, isothermal, Acerbaric, and Acerbaric. You can immediately see that for an adiabatic process, because dQ is 0, then C is 0. For a isothermal process, dt is 0. So what if, a finite amount of heat flows into a system, yet the temperature remains constant? In that case, C is undefined. For the other two processes, constant pressure or constant volume, we have well-defined heat capacity. In a constant pressure process, it's called Acerbaric. C sub P is equal to dQp over dt. Over here, this P in the subscript denotes constant pressure or Acerbaric. So in this case, this C is well defined. And dQp is an exact differential. dQp can be integrated. In a constant volume process, we use C sub V. It's simply dQv over dt. Or we can use a different notation over here to emphasize this V is constant in the subscript. Again, dQv, like dQp, is an exact differential and can be integrated. Cp and Cv are extensive variables because they are proportional to the size of the system. However, if you divide Cp and Cv by the number of moles, you get Cpm and Cvm. They are intensive properties. For ideal gases, Cp minus Cv is Nr. Cpm minus Cvm is R. And you can see this is extensive. This is extensive. These two are intensive properties. The difference R is also intensive properties. Cp and Cv are both extensive properties. Therefore, Nr is also an extensive property. Nr is obviously proportional to the size of the system. As N increases, Nr increases. Why is there a difference between Cp and Cv for ideal gases? Very simple. When we try to increase the temperature of an ideal gas by 1 Kelvin, more heat is required in the isobaric process because work is done to the surroundings during the isobaric expansion of the system as the temperature increases. In the isochoric process, however, work is 0. The system does not do work to its surroundings in the isochoric process. Therefore, more heat is required to increase the temperature of an ideal gas in the isobaric process than in the isochoric process. Now let's look at the heat capacity from the molecular level perspective. In quantum mechanics, all molecules occupy discrete energy levels. Now let's look at the translational, rotational, vibrational, and electronic energy levels. So the same molecule may occupy, this translational energy level and that rotational energy level. Okay. So it's possible for a molecule to occupy the lowest vibration energy level, yet the second lowest rotational energy level and the fifth lowest translational energy level. So they are different. When heated, it's easier to move molecules from the lower translational energy level to the higher translational energy level. Why? Because the energy spacing between translational energy level is really small. It's roughly 10 to the power of negative 30 or even 10 to the power of negative 40 joules. It's a bit more difficult to promote molecules from lower rotational energy level to higher rotational energy level. But still, it's very easy at the room temperature. However, at the room temperature, it's very difficult to move the molecules from the lower vibrational energy level to higher vibrational energy level, not mentioning electronic energy levels. So because of that, at around the room temperature, the translational molar heat capacity under constant volume condition is 1.5 R. Again, when the energy spacing is small, we will see in each dimension the heat capacity is 0.5 R if the energy spacing is small enough. And when we talk about translation, there are three different types of translation in three different directions: X, Y, and Z in a three-dimensional world. Therefore, the translational CVM is 1.5 R. If you imagine there is a four-dimensional universe, in that universe, the translational CVM is 2 R. Now let's look at the rotational CVM. For typical nonlinear molecules, CVM is also 1.5 R because the molecule can rotate about the X, Y, and Z axis. In each rotational dimension, you have 0.5 R. However, if you have a linear molecule, it can only rotate about two different axes. Therefore, the CVM for a linear molecule is usually just R. How about vibration? It's very difficult to change the occupation number in vibrational energy levels. Therefore, the CVM of vibration is typically much smaller than R and is often negligible. For example, if you look at HCl at the room temperature, the CVM of vibration is roughly 0. The electronic heat capacity is always negligible because, again, the spacings between electronic energy levels are just too large. It's almost impossible to promote molecules from lower electronic energy level to higher electronic energy level. At very high temperature, molecules may be promoted from the lowest vibrational energy level to higher levels, and in that case, the CVM of vibration may become significant. There's another possibility to have non-zero CVM of vibration. That is when the vibrational frequency of the molecule is very small, such as iodine 2. The vibrational frequency of iodine 2 molecule is very small. Therefore, it's easier to promote the iodine 2 molecules from the lower vibrational energy level to higher vibrational energy level. So let's look at a few examples. Argon, let's say 15 degrees. Its CVM of translation is 1.5 R. That of rotation is 0 because it's an atom. It does not rotate. There's no vibration. So it's exactly 0. Therefore, the CVM of argon is 1.5 R or 12.5 joule per mole K. This number matches exactly with the experimental value. Now nitrogen 2 at the same 15 degrees temperature, roughly room temperature. Its translation CVM is 1.5 R. Rotation, it's a linear molecule, so it's going to rotate about two different axes. The CVM of rotation is 2 times 0.5 R, it's just 1 R. its vibration CVM is nearly 0. This is because the bond between the two hydrogen atoms is strong. The vibrational frequency is really high. It's very hard to promote nitrogen molecules from the ground vibration energy level to the first vibration energy level. Alright, so in this case, we predict the CVM of nitrogen 2 is simply 1.5 R plus R. It's 2.5 R or 20.8 joule per mole K, which also matches with the experimental value really well. So what about the difference? There's a very small difference, 0.2 joule per mole K difference. I think that's due to the small CVM of vibration. It's nearly 0, but not exactly 0. Now let's look at a nonlinear molecule. It's H2S. Okay, it's sulfur hydride. Same temperature. Again, the translational CVM is 1.5 R. Now the rotation is 1.5 R. It's nonlinear. This molecule can rotate about the X, Y, and Z axis. So the rotational CVM is 3 times 0.5 R. What about vibration? Nearly 0. Therefore, we predict the CVM of this H2S is roughly 3R or 24.9 joule per mole K. It's also a little smaller than the experimental value. It's the difference is roughly 0.5. I think that's also due to the non-zero vibrational CVM. It's nearly 0, but it's not exactly 0. Now let's look at SO2. It's also nonlinear. It has a band structure. Well, the CVM of SO2 is 31, much greater than H2S. What's going on? Very simple. Actually, in SO2, because its vibrational energy level spacing are much smaller, this time you observe a greater value of the vibrational CVM. Okay, so that's why. This statement is fairly useful. I want to say all monatomic molecules have a CVM of 1.5 R. Why? There's no rotation, no vibration. So if you see a monatomic gas like helium, argon, neon, I can tell you the CVM is just 1.5 R exactly, or roughly 12.5 joule per mole K. For diatomic molecules, typically it's 2.5 R. Why? 1.5 R from translation, 1 R from the rotation. Maybe a little bit from vibration, such as iodine 2. Okay? Nonlinear molecule, 1.5 R from translation, 1.5 R from rotation, and some from vibration. So usually it's 3 R or higher than 3 R. Now you got a table of the CVM of different gases. You can see monatomic, it's just 1.5 R. Diatomic is roughly 2.5 R, except for chlorine. Chlorine, this one is bigger than 1.5 R. Again, this column is CVM over R, so it's nearly 3 R. Why is that? Again, the vibrational frequency of chlorine 2 is smaller than all other diatomic molecules. So it's possible to promote chlorine molecules from the lowest vibrational energy level to high levels. Therefore, the vibration also make contribution to CVM. In the case, roughly 0.48 R is from vibration. Triatomic, now really there are more vibrational modes that all make contribution to CVM more or less. Therefore, this H2S is fairly close to 3 R. In this case, the vibration made only 0.06 R contribution to CVM. And if you look at SO2, more contribution, CS2, it's nearly 5 R. Again, this is because the vibrational CVM is now significant for CS2.